Okay, we have been discussing properties of polymers, and we started with discussing thermal, mechanical and viscoelastic properties. These three properties, thermal, mechanical and viscoelastic properties, are very related to each other, that is why they are clubbed together. And in this lecture I will discuss about mechanical properties, and then we will start the discussion on amorphous state of polymers. So, let us begin with mechanical properties. Now, polymers, the advantage of polymers, that polymers provide very good mechanical properties at reasonable cost. That is why polymers are used everywhere nowadays, because at a cheap price we can get a good mechanical performance from polymer products. The factors that influence mechanical properties are chemical composition, molecular weight, branching, cross-linking. These are the property or characteristics are for the polymer itself. So, basically the chemistry of polymer which gives these properties, or the chemical composition, molecular weight, branching. So, you can control these properties during synthesis of the polymer. Once synthesis is done, you have no control on these parameters, unless you are using a reaction molding type processing later on, which are not very common. Other properties like crystallinity, orientation, these are also affect mechanical properties, and these properties like crystallinity, orientation, they depend both on the polymer chemistry or chemical composition of the polymer, also on the processing, polymer processing steps, how you are carrying out the polymer processing. The mechanical properties also depend on if somebody add plasticizers or fillers or other additives, they are basically added on the polymer samples. Of course, the performance, mechanical performance of the final product depend on the processing history and sometimes thermal history of a particular sample, other than this all these parameters which I discussed. But even all these parameters are same for a particular product, the mechanical property or mechanical performance of that particular sample can be dependent on the temperature of the testing and the time scale, how fast the testing is done or how slower this testing is done. So, this is dependent on the testing process. So, the mechanical performance or value of the mechanical properties also will depend on the temperature and the time scale, and this dependence is a consequence of viscoelastic nature of the polymers. What is viscoelastic nature? Viscoelasticity implies that the material has the characteristics of both a viscous liquid and an elastic solid. Viscous behavior means that if we apply stress or apply force to a material, it cannot withhold the stress without flowing. Like if I tilt a water bottle, water will flow, it will not be able to sustain the force, gravitational force which have been acting on it, and once it flows, it will be permanently deformed. It will not by itself come out to the original shape. That is viscous behavior. Elastic behavior is when a sample or a material is deformed, as soon as the force or the stress is removed, the material will come back to the original state on removal of the applied stress. So, that is a example of perfect elastic material. A polymer can have both viscous or elastic behavior depending upon the temperature or the time scale of the experiment or testing mechanism you are using. Now, there are different types of deformation possible for a plastic material or polymer material. Elastic deformation, as I explained, that elastic deformation is said to have happened when the material returns to its original state on releasing the stress following the same stress strain curve that it took during deformation. So, while deformation it took a particular shape or particular path of stress strain path, then when you remove this strain it will come back using the same path. That is a perfect elastic deformation. So, there is no loss of energy. They apply whatever energy you applied, you can get it back. Inelastic deformation is where there is a possibility that the sample will return to the original state, but in case different route, and there is a possibility or indeed there will be some loss of energy or partial loss of energy. The third deformation type of deformation is plastic deformation. In this case, the sample will deformed permanently and it will not be able to come to the initial state, and that happen a point called yield point, where the material starts showing plastic deformation. Mechanical properties of a polymer material or plastic materials, there are different types of test one can do, like statics test, which gives tensile, compressive, shear test. They give stress strain behavior, stiffness, strength and toughness of a material. Impact test, like high strain properties, it gives the impact strength of a material. Creep test, it gives time dependent elongation of a material. Also it gives the parameters of viscoelasticity. Dynamic mechanical test gives viscoelastic properties, the values for thermal transitions like Tg, Tm, molecular relaxation. Fatigue test is applied when lifetime or durability, one need to find out the lifetime or durability of a particular sample in a particular application. Hardness gives the resistance to surface indentation. Abrasion resistance is a measure of the weight loss by a abrator or a finely divided abrasive. So, basically you can see there are many tests that are available for a engineer or a product specialist. Now, which test needs to be done, that will depending upon the final application for the material. If somebody wants to find out the say scratch resistant or mar resistant of a plastic film, then he should or she should do a hardness measurement. And if somebody want to use this structural material, then stiffness is a very important property. If somebody wants to use for long duration in a some application, then fatigue test must be done. So, basically depending upon the application, the application engineer or polymer engineer should select the type of or more than one type of test to find out the mechanical performance of a polymer sample. Some basic definitions about on mechanical properties. Stress is the force divided by the area upon which the force is acting, and strain is the change in dimension divided by the original dimension. And there are different types of stress, like in this case a stress is applied in a longitudinal direction, and this is called tensile stress, and the deformation happens in a longitudinal direction, or the length is increased in this case, and so the strain is called tensile strain. In this case the force is applied in one direction, keeping one of the side fixed. So, the deformation happen sidewise or horizontally. So, this is called a shear stress, and the deformation happen is called shear strain. So, depending upon type of sample or type of force, we can have different types of strain and different types of strain. Two examples are given here, tensile and shear. There are other possible deformations in various modes like tensile as I mentioned, shear I mentioned. There could be other type of shear where we are basically applying a circular force. If the compression is happening by applying force like this, the way it is shown, this is compressive stress. This is a flexural stress where these two sides are fixed or supported and a force is applied in the middle. So, basically it bends after applying the force like this dotted line, and this is called flexural stress, the force per area, and this strain is called flexural strain. Similarly, in this case these samples are fixed one end and there is a oscillatory stress is applied, oscillatory force is applied this way, this way, this way or up and down. So, in this case we are talking about oscillatory stress or oscillatory strain. So, again depending upon the application of the final product, we need to or somebody need to basically identify which type of deformation mechanism he or she should choose to find out the performance of a material. For example, let me discuss about tensile testing, and as I repeatedly saying that in the lab we cannot basically make the final products like a car headlamp or any buckets, or there are several things we can imagine. We cannot make all those products in the lab. So, what we do in the labs, instead we make some standard sample, and the standards are mentioned given by different standard organization like ASTM, ISO. ASTM means American Standard Organization or International Standard Organization, ISO, and they give a specific dimension of the sample that need to be molded and a specific condition, test condition that need to be followed to generate meaningful data which can be used to compare or used to predict the performance of the final polymer. In this particular case, ASTM 630, it is a test is used for measuring tensile properties. In this case, a sample is formed and then a constant strain rate is applied. This sample is deformed with a constant strain rate, and the resulting stress is measured and stress is plotted against the strain. So, typically a dog bone shaped sample is molded and these dimensions are all specified by this standard test. These are all given and these are available in literature, and once this material is molded in a particular shape, it is taken to a equipment or instrument we call a strain instrument or instron or universal testing machine, and it is pulled in a longitudinal direction. So, we are talking about tensile test at a constant strain rate, and the stress, the resulting stress or the required stress is actually measured by this machine, and stress is plotted versus strain. The sample is deformed, pulled at a constant rate, and the stress force by area is monitored. Fixed shape, size, environment, standard methods, as I said, that these methods, what is the size of the sample, what is the environment, what is the temperature, these are all need to be followed as per the standard which is mentioned in the standard testing protocol. The stress will depend upon the area or cross sectional area of the sample, and the change in length will depend on the original length. Now, as the sample is pulled, the cross sectional area will change, so as the length. Hence, the force or the stress actually keeps on changing as the length of the sample increases, so as the strain, value of the strain. Hence, if we plot stress and strain, which are also function of the moment that when we are measuring. So, we define engineering stress, which is the load or the force divided by the original cross sectional area, but the true stress, which varies at different time, depends upon the force, applied force divided by the cross sectional area at a given time, which keeps on changing as we increase the length of the sample. Similarly, engineering strain is the change in length divided by original length, and true strain is the change in length divided by the length at a given time. So, the length will increase as the time increases. So, per unit length increase in the length will have lower strain if the length but denominator value changes. True stress and true strain are the true or real stress or strain experienced by the sample, whereas engineering stress and strain does not account for the variation in the cross sectional area and the length with time, as I discussed. Now, this is the outcome of a tensile testing, a stress strain curve. In this case, stress is plotted in the y axis and strain is plotted in the x axis. As I described, the sample is strained at a constant rate and the required stress is plotted in the y axis. Now, at the beginning, up to a certain strain, this deformation is elastic deformation. That means, if we leave the stress, it will come back to the original shape. So, this limit is for this particular experiment is up to this point. So, this is the proportionality limit, and the slope of this stress strain curve is the modulus. In this particular tensile test, we call elastic modulus, which is given from the slope. Now, when we strain above this point, there is a deformation, but in this case, if we leave the strain or release the stress, then it will come back to the or may come back to the original shape, but in a different path. So, this is the example of inelastic deformation. After some stress, particular strain, there is a possibility depending upon the sample. Basically, some sample may break here, some sample may actually form a neck here, and when you apply further force, then this will get the neck will become bigger and bigger, and there will be little force which required now to elongate this neck. So, basically the stress almost remains same and the sample becomes elongated as shown here, and once this elongated quite a extent, then it require much more strain to further elongate, and this is called strain hardening. Now, this is the force or the stress it requires initially to overcome the intermolecular forces between the polymer chains. Once it overcomes, then polymer chains can easily move, that is why you require less strain. But at this moment, when polymer chains are elongated enough, then elongating the chains further, it becomes much more difficult. So, we require much more stress to elongate further, and this is the point where it breaks, and this value is called ultimate stress, and this corresponding strain value is called the strain at break or ultimate strain. So, this value corresponding stress is called ultimate stress, and this corresponding strain value is called strain at break or ultimate strain. This corresponding point is called yield stress, and of course, the strain corresponding is yield strain. This is the point where this necking start place, and once this necking happens, then it becomes easier for further elongation till it gets elongated to a such a extent that further elongation becomes much more difficult, and this is the region we call strain hardening. So, this region is elastic deformation, this part is non-linear elastic deformation or inelastic deformation, and this entire region is plastic deformation. So, if any time we release the stress from this point or this point or this point, it will not come back to the original state, whereas if we release the stress from this point, it will come back to this original point. If we release the stress from this point, then it may come back, but in a different path. We will now learn about the different other different parameters who form this stress strain curve. So, as we shown here, this is the yield stress. So, this is yield stress, and these are the very common term we come across. Stiffness or rigidity, it means the ability of the material to carry stress without changing dimension, and it is given by the value of stiffness or rigidity, or quantification of rigidity or stiffness is obtained from the value of elastic modulus. So, if the elastic modulus is higher, we say the sample or the material is stiff or very rigid material. So, when we say stiffness or rigidity, we must remember what is the underlying property we need to quantify. In this particular case, elastic modulus need to be quantified. Similarly, when you talk about elasticity, is the ability to undergo reversible deformation to carry a stress without suffering permanent deformation. So, basically till the yield point we have elasticity. So, it basically gives the, so up to this strain it gives the elastic limit. So, if the stress or the strain before yielding happens is higher, then we call that the elasticity is higher for that particular material. Similarly, strength, when you say the material is having high strength, this means the ultimate strain ultimate stress, this value this is the, so this corresponds to the ultimate stress. So, value of this is what determine the strength of a material. So, higher is the value of tensile strength or ultimate strength, that is given by the higher value of this particular stress. So, when we say a material is having high strength, we will know that it has a having higher tensile strength or the stress which at which the specimen ruptures. Similarly, when you talk about toughness, toughness is the energy spent in causing a material to fall or fail. So, basically at this point the material breaks. So, before it breaks, how much energy it has absorbed, and this is given by the area under this stress strain curve. So, this area is gives the toughness of a material. The higher is the value of this area, it gives the toughness of the material. So, when you say a material is tough, that means it consumes or it absorbs much more energy than a material which is less tough before it breaks. And this value, the elongation at break, which is generally represented as a percentage, is sometimes also used to quantify a term called ductility. Ductility, LITY. So, basically the higher is the elongation till it breaks, we call that sample is highly ductile. It is generally been seen that the samples which have having high modulus, they are low ductile, and the sample which are highly ductile, they having low modulus value or more low stiffness value. For example, elastomers have highly ductile property, high elongation, but they can resist very little force. So, their stiffness is higher lower. Similarly, fiber, the stiffness is higher, but elongation is lower. So, it is very difficult to make, it is always a challenge and remains a challenge to make a material which is having high modulus and ductility in a particular sample. Now, let us compare some of the young modulus value or tensile modulus value for different materials. Polymers are having lower than metals or ceramic, but composite, but if we compare the modulus divided by the mass, then polymers will having higher. So, basically we can get more stiffness or more mechanical performance from a for a given amount of material in case of polymer, that is why it is useful. And so, if you typical stress strain curve, ceramic will look like this, metal will look like this, and polymers will look like this. So, compared to metal and ceramic, polymers having low modulus, but higher ductility. There are other types of mechanical test, and that will depend on the type of material which higher type of application. For example, impact test is to quantify when something come across impact, like a car is sometimes hits something and then it is basically a sudden impact. So, to test the material's capability to resist or this impact force, the different types of testing are done, they are called impact test, and there are different type of impact test, again depends on the final application of the polymer. For example, this is called Charpy impact test, where one notch is made in this type of sample, these are fixed here and one hammer is heat into this, and the samples is broken, gets broken in this area. Simple another test is notched isotope test, where the a sample is make in this with a notch, and these are fixed on this part, and hammer is hammered on the top part, and the amount of energy which is required to break this upper part is called notched isotope impact strength. And in fact, depending upon the surface of this broken piece, we can actually detect the type of failure, whether it is a ductile failure or a brittle failure these materials. Okay. If the energy required to make or break this sample is high, typically it basically represents a ductile failure, and you can see the surface of the broken piece. I am not going in detail on those tests. Similarly, there are tensile impact tests. The test is done as shown here using a tensile sample. Another test is like falling dirt test, and there are some other tests like Dynathrop test and all this. Those are basically tuned or designed or tailored as per the final application requirement for the particular sample. So, right impact test based on the stress state and right condition, loading rate and temperature need to be selected based on the target application while screen the candidate for material. This is another information which we might require is Poisson ratio, when we basically as we discussed for engineering stress and screw stress, as we use a tensile force, then the width or the cross sectional area might change. Generally, as we elongate a sample, generally it decreases, the cross sectional decreases, and Poisson's ratio is defined as the width strain, the how much deformation happened in the width corresponds to the in terms of original width divided by the axial strain or the strain in the longitudinal direction. So, change in width divided by original width, and this is change in length divided by the original length, and the minus sign because this is generally in opposite direction. To make this number positive, there is a minus sign, and typical values for metal are metal, ceramic and polymers are shown here. Obviously, this is a unitless quantity, and the units for modulus are in Pascal or in gigapascal or megapascal and or in PSI. So, we will next move to thermal properties of polymer, and as I said that mechanical properties and thermal properties are related to each other, and we need to understand the thermal properties to it is very important in terms of processing as well as product performance, and as I said that it is interlinked with mechanical, rheological and rheological behavior. So, in next class I will start from here and discuss thermal properties of polymer.